first carbon atom which are differ only in the position of the hydroxyl group. They are known as anomers. The CH2OH and CH2OH on both the sides. Why is it like that? Because here you can understand that the fifth carbon atom will be get added up with the OH, that is hydroxyl group. So what is the glycosidic linkage or the glycosidic bond? It is a bond between the two monosaccharide unit through the oxygen. Hello my dear students, a warm welcome you all. Myself is Purnima, lecturer in Department of Chemistry at Vidhyaashram Pre-University College, Temple of Excellence, Mysuru. My dear students, in our last discussion, we were dealing with the unit called Biomolecules. Under that, we have discussed about the introductory part to the carbohydrate, and we have understood that the classification of carbohydrate, and also we have learned how do we prepare the glucose, and we have understood with the structure of glucose. Today, let us move on to the next topic of this unit about the cyclic structure of glucose. In that, we are going to understand what is the different cyclic nature of glucose, and we are going to write the Harvard structure for the glucose, and finally we are going to discuss with the fructose, and in the disaccharide we are going to discuss with the maltose and lactoses, and in the polysaccharide also we are going to discuss with a few examples. Okay. So let's see what is a cyclic structure of glucose. So we all already know that the glucose, which is having a molecular formula C6H12O6. And from the following observation, as we have already learned from the Fishner, so the glucose molecule which is present in a straight chain where all the carbon atoms are linked together forming a straight chain. Is it right? And how to explain this cyclic behavior of the glucose? Let us understand now. So the glucose that do not give Skiff test and do not react with sodium bisulfite and with the ammonia. If you check the glucose with the sodium bisulfate and ammonia as well as with the Skiff reagent, it do not shows any reaction. And the glucose which is found to exist in two crystalline form, they are known as alpha and beta, and alpha form of glucose which is obtained by crystallization from concentrated solution of glucose at 303, where beta form of glucose are obtained by crystallization with the hot and saturated solution at 371 Kelvin. So that is very important to know it. Remember, the glucose molecule which exists in a two form, that is alpha glucose or alpha form and beta glucose. Is it right? Alpha glucose will be obtained by taking the solution at 303 Kelvin, we can crystallize it. So this is a crystalline form of glucose which is obtained by taking the concentrated solution of what? Glucose and maintaining the temperature around 303 Kelvin. Whereas a beta form which is also obtained by the crystallization of saturated solution of the glucose at 371 Kelvin. 371 Kelvin. So it is very important to know that the glucose will be exist in a two different form. Next thing is the behavior could be explained by open chain structure of the glucose. It was found that glucose forms a six-membered ring in which OH at fifth carbon atom involved in the ring formation and explain the absence of CHO group, and also the existence of the glucose in the two form are shown below with the two cyclic form which exhibits the equilibrium. You can see that this is our glucose, and this is the first carbon atom, second, third, fourth and 5. This fifth carbon atom which are having the OH group, which will be moved towards this oxygen, so that the double bond between these two will be removed out and results in a formation of bond with the first carbon atom along with the fifth carbon atom, where oxygen bond will be formed. So this is a alpha D glucose, and you can see here, if you write the OH on the right hand side, it will become alpha D glucose. If you write the OH on the left hand side, it will become beta D glucose. This is how we can obtain the two forms of glucose, that is the alpha form and a beta form, by doing the crystallization. Hope you all understood with this topic. Here I have written the glucose structure, where my carbon at the fifth position which are having the OH, which forms a bond with the first carbon atom, so that it will form a alpha and a beta glucose. Is it right? For this case, how to write the Harvard structure? So what happened, the scientists, they have compared the structure of the glucose with pyranose, which is a 6-membered ring. So anomers are nothing but a 2-cyclic form of glucose, which are differ in the configuration of hydroxyl group at a C1. They are known as anomeric carbon atom. You can see that the first carbon atom, which are differ only in the position of the hydroxyl group, they are known as anomers. And remember, the 6-membered cyclic structure of the glucose are also known as pyranose. They are also known as what? Pyranose. This is the structure of the pyranose. So what they have done, once they come to know that this glucose can be exist in a 2 form, that is alpha and a beta form, they have written the Harvard structure for this by taking pyranose as a reference one. Okay, how to write this? We know that the pyranose which will having a oxygen, and it is a 6-membered ring. So here for the alpha D glucose, I'll write pyranose to the first carbon atom. You can see that OH group will be present. So I'll write down. Okay. Similarly, the second carbon atom which is having OH. Third carbon atom is having H. Is it right? Fourth carbon atom is having OH. Fifth carbon atom which is having CH2OH. Is it right? So it is written in the upside because CH2OH is a bulky group. It cannot fit into the inside. So, and remaining H, OH, H and H. This is how we can write the alpha D plus glucose, and it is named as glucopyranose. Why is it so? Because you are writing this glucose structure in the pyranose form. Hence it is named as alpha D glucopyranose. This is how we can easily write the glucose structure in the Harvard form. You can write for the beta also. First I'll write the pyranose. So what is the first carbon atom which is having H, OH, H and OH. And again this is CH2OH, H, OH, H and OH. This is beta D glucose pyranose. Glucopyranose. This is how we can write the Harvard structure for the two forms of the glucose, that is alpha D glucose and a beta D glucose. Again I have written here the same kind of structure what I have written. Here I have written the Harvard structure of the glucose. So you can see that OH, OH, OH and H. Similarly, OH, OH, OH and OH. How to remember this structure? This can be remembered as, so it is present in the down. Is it right? Down, down, up, down. Down, down, up, down. So this is how you can easily remember that how the OH group which I have written on the pyranose structure, that is down, down, up, down. Whereas in the beta D glucose, which is the reverse of alpha D glucose form, and it is named as alpha D glucopyranose or glucose pyranose, you can write full name. So or you can write beta D glucopyranose. So it is very easy to remember. What is the tricks here? That is down, down, up, down. This is how we can easily remember the pyranose structure for the glucose. Next thing is about fructose. Let's see what is a fructose and what is the structure of the fructose. Fructose is a ketosis, and we know that glucose is a aldoses. Is it right? Yes. So fructose is a ketosis and it is obtained along with the glucose by hydrolysis of sucrose. So the fructose, which also having a molecular formula C6H12O6, and it is a ketonic functional group at carbon 2. So at the carbon 2, you can see that there is a ketonic functional group will be there in the fructose, and it has a 6 carbon chain or 6 carbon atom in a straight chain, and which is belonging to D series, and but it shows that it is levorotatory. Why it is levorotatory? Because this portion already have explained with the glyceraldehyde, which shows the negative form, hence it is levorotatory. It is approximately written as D minus fructose, and it is a open chain which I have written. It also exists in 2 cyclic form which are obtained by addition of OH at carbon 5 and the COO groups. In this, the 5-membered rings are named as furanose with the analogy of this compound furon. Okay. So what is the structure of this fructose? You can see that there are 6 carbon atom will be there, but to the second carbon atom which consists of a keto group because it is a ketosis. Okay. Whereas our glucose, which is having a aldoses and having a aldehyde group at the first carbon atom, and remaining OH and a H I have written. This is how we can easily remember the structure of fructose. Why it is levorotatory? Because the last portion which is similar to the glyceraldehyde, already we have learnt why it is shows a positive structure and a negative structure also. Let's see with the 2 forms of the fructose, that is alpha D fructose and beta D fructose. This is the structure of the fructose, and you can see that the 5th carbon atom, where it usually get added with the OH and forms a bonding with the 2nd carbon atom and forms a alpha D minus fructofuranose and beta D fructofuranoses. Now I'll write the structure of furon because it is a 5-membered now. Let's see how to write the our structure, that is OH, H, OH and it is CH2OH. Okay. So it is H, OH and H. This is alpha D minus fructofuranose. Whereas for this, OH, H and OH and CH2OH and H. This is beta D fructofuranose. Fructofuranose. You can understand here. You can see that the first carbon atom which is having OH, OH and OH. So it is down, up, down, down, up, down, and I have written the CH2OH and CH2OH on both the sides. Why is it like that? Because here you can understand that the fifth carbon atom will be get added up with the OH, that is hydroxyl group. That is why I have written CH2OH directly. Here also you can write, this is a negative form of the alpha D. So that is why I have written at the down CH2OH, OH, OH and OH. This is up, down, which is the opposite. Okay. This is how we can easily write the Hawa structure for the fructoses also. Okay. And remember, while writing for the fructoses, we are using furanose, not with the pyranose. Next is disaccharide. Disaccharides upon hydrolysis, we know that it is a 2 monosaccharide units. The molecules are held together by a glycosidic bond. What does it mean? It is a linkage between the 2 monosaccharide unit through the oxygen. So what is the glycosidic linkage or the glycosidic bond? It is a bond between the 2 monosaccharide unit through the oxygen. So we will understand that how this disaccharide will be formed by taking the example of sucrose. So sucrose is an disaccharide, and upon hydrolysis, you know, it gives an equimolar mixture of glucose and fructoses. Okay, and these 2 monomers or the monosaccharides are held together by glycosidic linkage through the oxygen and forms alpha glucose and beta fructoses. Okay, so you can see here, this is my sucrose. Upon hydrolysis, you know, it gives to D-glucose and D-fructoses. Okay, next thing is, I have written the structure of fructoses where it forming a 2 monosaccharide unit upon hydrolysis. So this is alpha D-glucose, this is beta D fructofuranose. We know that the glucose will be exists in the 6th chain, whereas our fructose will be exists in the 5 carbon chain. Is it right? That is why I have written this Hawa structure of the glucose and fructose by taking pyranose, and it is a furanose. And we know that these 2 monomer units are joined together by a glycosidic linkage, that is oxygen. So this is how, you know, we can represent the structure of sucrose. Next thing is about sucrose. Sucrose is a non-reducing sugar. Since the non-reducing groups of glucose and fructoses are involved in glycosidic bond formation. So why they are forms a bond? Because of the non-reducing groups in the glucose as well as in the fructose. So this sucrose is also known as what? Invert sugar. Why is it so? Because the sucrose is a dextrorotatory, but upon hydrolysis give a dextrorotatory glucose and levorotatory fructose. The levo-rotation of the fructose, which is more than the dextro-rotation of glucose, thus the mixture of levorotatory and thus the hydrolysis of sucrose are being brought about a change in the sign of rotation from dextro to levo, and the products are named as invert sugar. You can see that I have written the sucrose. The formula is C12H22O11. Upon hydrolysis, what does it form? It forms a dextrorotatory glucose and levorotatory fructose. And you can see that they are having a rotation range around 52.5 and there it is 92.4, and it is more for the levo-rotation of fructose. Hence, it is known as invert sugar. Next is maltoses. So, maltose is composed of 2 alpha D glucose unit. So, I have written the 2 alpha monosaccharide units. Okay. The C1 of the glucose is linked to the C4 of the other glucose unit. The free aldehyde groups can be produced at C1 of the second glucose solution and shows a reducing property, and it is a reducing sugar. You can see that the first carbon atom and the fourth carbon atom, they are involved in the formation of bond. Is it right? They are involved in the formation of bond and it forms a what? Maltoses. Remember, this is a alpha D glucose, and there is another alpha D glucose where the first carbon atom and the fourth carbon atom are involved to form a bond, and hence it is known as maltosis. Next, I have lactosis. It is commonly known as milk sugar. It is composed of beta D galactose and beta D glucose. It is made up of what? Beta D galactose and beta D glucoses. The linkage will be happens at C1 of the galactose to the C4 of the glucose. This is a C1 of the galactose and this is a C4 of the glucose. They are held together by a glycosidic linkage. Okay. Next is polysaccharide. Already we have understood that polysaccharide in the sense during hydrolysis it forms a large number of monosaccharide units. Is it right? Yes. Polysaccharide which contains large number of monosaccharide unit, they join together by a glycosidic linkage. The best example is starch. Is it right? That is C6H10O5 upon hydrolysis which gives rise to the glucose. This is the best example for the polysaccharide. So the starch is a main storage polysaccharide in the plants and it is most important dietary source for the human beings also. It is a polymer of alpha D glucose and consists of two components, that is amylose and amylopectin. What does it mean? Let's see now. It consists of what? Two components, that is amylose and amylopectin. Amylose is a water-soluble component which constitutes about 15 to 20% of starch, and chemically amylose are long unbranched chain with 200 to 1000 alpha D glucose held together by C1 to C4 at glycosidic linkage. So what is a amylose? These are the soluble component of the starch and it consists of 200 to 1000 number of alpha D glucose especially linked at carbon 1 to carbon 4 by a forming a glycosidic linkage. Whereas amylopectin, these are insoluble in water and constitute around 85% of starch and it is branched chain polymer of alpha D glucose units in which the chains are formed by C1 to C4 by a glycosidic linkage, whereas the branching occurs at C1 to C6 by a glycosidic linkage. So, when I say it is a amylose, remember it is a soluble part, whereas amylopectin it is an insoluble part and it constitutes around 80 to 85% of the starch. Here I have written the structure of the polysaccharide. So, these two are the glucoses. This is the alpha D glucoses. You can see that in case of the first and the fourth carbon atom, they link together by oxygen atom by forming what? Glycosidic linkage. Similarly, if you see with the amylose pectin, the first and fourth carbon atom, they held together by oxygen atom and forming a glycosidic linkage. Like this, the process will be observed. But you can see that the first carbon atom and to the sixth carbon atoms, you know, the CH2OH, it forms a bonding and it forms a branched starch. It forms what? Branched structure in the starch. Hence, this is known as branching at carbon 1 to carbon 6 we can see. Hence, this is a special case in the starch. So, hope you all understood. I have talked about the amylose, amylopectin. If there is a branching, in which carbon atom it is occurs from C1 to C6. Okay. If it is in the normal case, glycosidic bond will be occurs between C1 to C4. Next is differences between amylose and amylopectin. We know that amylose is a large unbranched polymers of alpha D glucoses and it is a long branched polymer of alpha D glucoses. Whereas amylose, we know that it is a water soluble and it is water insoluble. And it constitutes around how much of the starch? It constitutes around 20 to 25% of the starch. Whereas amylopectin would constitute around 80 to 85% of the starch. And monomers units, which means to say that the monomers in the structure. They link together by C1 to C4 by a glycosidic linkage, whereas monomers will also here link together by C1 to C4. If there is a branching, it will occur at C1 to C6. As I have explained in C1 to C6, if there is a common amylose, it will be branching will be occurs at, or you can say that glycosidic linkage will be occurs between C1 to C4. If it is a normal amylopectin, here also C1 to C4, a common glycosidic linkage will be moves on. But if there is a branching, then glycosidic linkage will be occurs between C1 to C6. So in the next session, we are going to deal more about the cellulose. Okay. So by this, I like to say that what are all the things which I have covered in this session, it is very important for the examination point of view, especially the Harvard structure will be asked to write it for the 2 marks. Have a look on it and try to focus on how to write on the Harvard structure. We'll meet you in the next session. Till that, take care and be safe.